Okay, so let's continue with the basics of probability again. So here we'll see the Venn diagrams. So in the last lecture, we saw what are the operations like union. So here you can see that shaded area that we have is the union of two events. So let's say we have two events E and F, and S is our sample space. So this shaded area in green is our union of these two events. Similarly, intersection is the common thing in between. So as you can see, the small shaded area. So this is the intersection of two events E and F, and this is the complement. That is, let's say if this is event E, then what is shaded is like rest of the area which is not in E, right? So this is the complement. So this is just a Venn diagram, basic introduction to it, and you will see that why I used in this very first slide, because we are going to prove some axiom in later section of this video. So let's move into axioms now. So now we will be purely mathematical. So let's say we have an event E of an experiment, and let's say the sample space of that experiment is S. So very first axiom is that the probability lies between 0 and 1. This we already know from our school days or high school or whatever. So but still I'm covering everything to cover all the audience, as I said. And similarly, the probability of the sample space is equals to 1, because we know that in sample space everything will be included, all possible outcomes will be there of an experiment in the sample space. So that's why this probability is 1. But let me don't frame it like this. Let me write some statements regarding what does this mean, right? So what this axiom 1 means, let me take a fresh page for that. And the axiom 1, what does it mean? Let me write that. So it states that the probability that outcome of an experiment is contained in E. So like we have one experiment, right? So there are all possible outcomes will be in the sample space N. But what is the probability that the outcome of that experiment, any experiment, let's say tossing a coin, is contained in E? That is the set of the event E, right? So that probability that we have will always lies between 0 and 1. This is what this axiom means. This will be more clear when I'll discuss about axiom 2. So what does this mean? Let me write that. So it states that with probability 1, because we have P of S equals to 1, right? P of S. So with probability 1, what we have to say, that the outcome of an experiment will be a member, or will be contained, let me use the same words as axiom 1, will be contained in sample space S. Because we know that sample space S is all possible outcome, right? So what is the probability that any random outcome, whatever we get of an experiment, let's say tail, will lie in S, because S is all possible outcomes, so it will be always there, right? And that's why we know that probability of certain event that it will be always there is 1. So this is the meaning of probability. The same thing that I wrote here, that probability that outcome of an experiment is contained in E. Let's say we have tail as our outcome, but in event E, right, there is head, then there are less chances, right, of it contain there are zero chances, because event E is just head and we got tail, right? So this is how the actual interpretation of this above statement means. Until now we just know that probability of any event lies between 0 and 1, but this is the actual meaning that I tried to explain. And now continuing to our axiom 3, it's also like really important. So this states that probability of union of all events. So let me write for just two events. Let's say we have two events E1 and E2. So what is the union of two events is summation of individuals, that is probability of E1 plus probability of E2, but if and only if. This means if and only if this all events, that is E1, E2 up till En, if we have n events, are mutually exclusive. And this we already discussed in one of our previous video, but let me discuss again and prove something regarding that. What are disjoint events? So let's say again we have two events, this time E and F, and let's say we have in E we have 1 and 2, right? Because and in F we have 2 and 3. This is visible from this Venn diagram, and this is our sample space S. So what can we write for union? We know what is union, right? In our very last lecture we discussed. So union will be all possible outcomes in both the events we have to take, and here you can see that all are mutually exclusive or disjoint. These are two same words, mutually exclusive, or we can also write as disjoint events. So why these are mutually exclusive? Because they can't occur like all the three events will not occur at the same time. That's why they are called mutually exclusive. So let me write what is probability of event E. So E will be just 1 plus 2, while we can write for F as 2 plus 3, correct? You can see here that, and also it's like intuitive that intersection, let me write that as well, that probability of E intersection F is what is common, 2 is common in between, right? So this is what we wrote. But now let us prove that probability, this you might know from your school studies, E union F is nothing but probability of E plus probability of F minus probability of E intersection F. And you can see from here, if you will add E and F, we will have 2 in common, right? So 2 will be this 2, I mean the Roman 2. This is common, right? So we have 2 times this, and we have to remove it once. And we know that this intersection is 2 as well. So if we subtract this intersection, it will be removed. So that's why we write like this. And this also proves that E and F are disjoint or mutually exclusive events, because if you add this two, uh, if you add E and F, then you get 2 like in common, right? So these are not mutually exclusive events. But what I want to say is that, so sorry, I said that E and F are mutually exclusive. It's not like that. These regions are mutually exclusive. All the three regions, region 1, then region 2, and region 3, are mutually exclusive. And that's why we can write like this. This statement can be written E union F equals to 1 plus 2 plus 3, because these three regions are mutually exclusive or disjoint. They can't occur together at a time. So sorry for saying that E and F are mutually exclusive. It's not like that. If they will be mutually exclusive, then we don't need this term. That's, their intersection will be null set, and we just have E union F equals to E plus F, which is our previous axiom, the axiom number 3, right? So this is what I want to say in this lecture. And from very next lecture, now we will be starting with the actual random variable. We'll see the intuition behind random variables, and again we'll move towards distribution, which are really important in terms of machine learning. So stay tuned, and we'll see each other in next video.